Welcome to Building Better, a podcast where we're going to cover everything you need to know about structural insulated panels. If you know a little or a lot about SIPs, or even if you don't know anything about them, don't worry. We're here to teach you and make it simple. Thank you for joining us in one more episode. Today we're going to talk about structural insulated panels, structural performance. My name is Gabriel Grossman. I'm your host today, and we welcome Engineer Mastermind to our podcast. He's passionate about structural engineering. He's licensed in 36 states, and he's dedicated to exploring innovative techniques in structural design, all with a keen focus on embracing environmentally sustainable materials and construction methods. He specializes in educational and high-end residential buildings, and of course, he's a SIP expert and has been designing buildings with SIPs for over 30 years. Troy Lesko, welcome to Building Better.
Hey, thanks for having me, Gabriel. This is an honor and a privilege, and I'm happy to talk about structural engineering of SIP panels all day long if you want to.
I appreciate it, Troy. I appreciate you taking the time to join us. So I think we can start telling our listeners just high level, how does SIPs compare to stick framing as far as structural integrity?
Yeah, let's start off with just a quick comparison contrast between SIP panels and stick construction. SIPs are very comparable to stud construction, especially with walls. So let's say, you imagine a stud framing. It's probably 2x6 studs. It's 16 inches on center. And for residential construction, the wall heights might be 8 or 9 or 10 feet tall typically. And SIP panels can basically be a substitution, like a straight substitution for stud framing in most areas of the country. What are the structural purpose of a wall? Well, you have to carry the load from the roof above or the floor above, or if you've got a multi-story building, then you're trying to support your roof and your floor framing with your walls. And, stud framing works very well. That's a tested method that's been used for hundreds of years. And SIP panels have been manufactured for about 40 years, maybe a little bit more than 40 years. And there's thousands of examples, tens of thousands of buildings out there with SIP panels as their walls. And it works very well. There's limitations that are published in your code reports, and testing has been done. It works very well. It's a very, very robust system. And we engineer, houses out of SIP panels all the time. Probably 500 projects every year. That's probably the first thing we should talk about is the bearing wall capacity of a SIP panel.
Wow, Troy, 500 projects a year. That seems like a handful. So how would you say they perform, right, in different loads, like in the transverse load? How much can the panel really span in your roof? I know it depends on the different design load criteria in different areas, but as an overall rule of thumb for our listeners, what can they expect as long as, the span it can hold up in the roof?
Yeah. So, switching over to roof panels, that's probably the second most popular structural element that SIP panels use for is the roof framing. So, SIP panels, they vary in thicknesses. We call it 4-inch, 6-inch, 8-inch. There's 10-inch, 12-inch panels. There's even some manufacturers that are making 15-inch thick SIP panels. But the actual thickness depends on the core thickness, because the idea is that SIP panels are made so you can integrate lumber or engineered lumber or I-joists inside of your panels. So really the core thicknesses are 3.5 inches, 5.5 inches, 7.25, 9.25, 11.25, and then 14-inch for your engineered lumber that's 14 inches deep. But wow, yeah, I mean, if you wanted to try to, let's say you're in Southern California, and you have a situation where you need to span your roof 20, 22, 24 feet, you can do that with a 12-inch thick SIP panel with no lumber in it. Just the strength of the OSB top and bottom skins with the EPS core provides enough structural strength to support those 20 pound per square foot live loads in areas where there is no roof snow load. So it's impressive.
That is impressive, Troy. And what about, we've designed some buildings together. What happens when the snow load goes over those 12 pounds per linear foot? Like, how do we design? We add, other structural members, and that can be LVLs or I-joists to be able to have that structure pass through the load requirements.
Yeah, it's a good question. And it comes up all the time. And, I'm based in Western Montana in Missoula, where the snow load is 30 pounds per square foot, but we're surrounded by communities that have a high snow load, 80 pounds per square foot up north in the mountains. As you move west into the Cascade Mountains and like the Lake Tahoe area too, there's designed snow loads that exceed 300 pounds per square foot, but that's kind of rare. If we were just to say that, we have a situation where we need to design the roof framing to support 100 pounds per square foot of snow load, then there's a couple of different ways you can deal with that. And because you wouldn't be able to span, your average 14 or 16 feet with an unreinforced sit panel. So you'd have to reinforce it with lumber or I-joists. And there's a lot of I-joist manufacturers out there. Let's say TJI, Boise Cascade, Louisiana Pacific. They're all making their I-joists. And I'm just talking about the normal I-joists that you would buy at a lumber yard to frame your floor with in a residential project. But we can reinforce sit panels with I-joists at 4 feet on center typically, and be able to achieve longer spans and or higher loads. And we can get up to 16 or 18 feet for a roof span if we put in lumber. Let's say, for example, if we put a double 2x12 lumber spline into roof panels at 4 feet on center, we could probably span 16 feet with a 100-pound snow load, in addition to the dead load, which is usually 15 pounds per square foot, sometimes higher.
Yeah, and for our listeners, here in Preflex, we have the option of pre-buying and pre-cutting and installing this lumber into their ready-to-assemble packets. So we're not just supplying them with the panels, but we're also supplying them with the lumber, as well as the structural design that we work with you and your team, Troy, at Eclipse Engineering. That's something that we can offer as well. And talking a little bit more on the wall assemblies, Troy, what is the highest, the tallest possible building that we can do with SIPs, considering that we can add additional structural members? And, what is the highest shear strength that they can hold?
Yeah, there's a few questions in that question. So let's unpack that. So walls are interesting because you have to combine loads in order to engineer a wall properly. And of course, one of the things you have to consider is the vertical load on the wall. So as a bearing wall, we are, for example, as I was mentioned earlier, supporting the roof framing. So let's say that you have, like 500 pounds per foot of load coming down on top of your wall. And at the same time, you have to engineer that wall to, support a wind load, like blowing transverse to the span of the wall. We call that out of plane loading. So, what's the maximum height you could span? We've definitely done 20-foot tall buildings. We've done maybe slightly higher than that too, but 20-foot tall buildings usually require an 8-inch panel. You can combine a relatively small roof load with a normal wind speed, and wind pressure, and make an 8-inch tall wall work for a 20-foot height. But you can also usually get a 6-inch wall to span 16 feet in height for your walls. And I'll just say this caveat too. This would be a normal wind conditions if you're on the Gulf Coast in the southeast United States, where you've got to design for hurricane type loads. They've got those 170 mile an hour, 180 mile an hour wind speeds. So that's going to affect things. But if we're on the West Coast and we're designing in California, it's usually pretty simple. to make a 6-inch SIP wall span up to 16 feet tall. I wanted to talk about shear walls too,
Yeah.
because that's another super important one, especially in California where you're in the high seismic areas. So yes, if we're thinking about, okay, well, what shear walls are we trying to substitute, SIPs for stud framing? Well, I'll just say that there's been a lot of testing done in third-party independent labs where SIP walls perform just as well as conventionally stud frame shear walls. It's just a matter of getting the nailing right and the hold downs right, the hardware and the fasteners. Usually with if you were to imagine an 8-foot long by 8-foot tall SIP wall that has a double top plate and a double stud on each end. If we put the nailing in right, which is, you can go as close as 8D nails at 2 inches on center, then the shear capacity on a SIP wall is as much as, I think it's 920 pounds per square foot, or 920 pounds per linear foot is what some of the test results have come out, which is huge. That's every bit as strong as a stud frame wall that's sheathed on both sides with a comparable amount of nailing. So once again, very impressive.
Yeah, I mean, that sounds very impressive. And I would also like to add there that the SIPs, us ourselves as Preflex, as well as the SIPA Association, have gone through a very prolonged series of tests for many, many years to prove these values. And these values can be found in the code reports that are published into building and residential codes. And they have their own specific ESR number where they can be looked up, and people and other engineers can find these structural values to be able to design using these components. So can we talk a little bit, Troy, about like the testing that has been done to the SIP panels throughout its history?
Yeah, sure. Gosh, I know that when it first started, and and the general public was it was a brand new thing. What are these structural insulated panels? I don't understand. It's, a 7/16 inch OSB facing on both sides and nothing except for foam in the middle. Does this really work? And so it had to be done. It had to be tested. And I believe the first tests that were done, this is before I even started my career in the 90s, but I've seen the results, and, it basically simply take some panels and of different lengths from, and span them over basically like blocks and all the other stuff you'd see in the laboratory, and then load it up with, first they were loading up with sandbags or, bags of water or pressure, air pressure, water pressure, and calculating what is, and then they would break them, load them to the breaking point. So let's say, for example, you had a 12-foot span of a SIP panel. You load it up till it breaks, and then and do that test several times, usually 3 times. And I believe there's an ASTM method for how to properly test a SIP panel in an independent lab. But you take the results, roughly divide it by 3, which should be our safety factor, and then publish the results in the tables in the code reports. So after hundreds and hundreds of tests, different manufacturers and the SIP and SIPA, Structural Insulated Panel Association, has created tables that were developed from actual testing in labs. And so there you go. And so it makes it super easy as an engineer to specify which panel spans and which panel thicknesses are safe on your buildings, because you simply look in the code report, go to the transverse load capacity table, and determine if your load exceeds your demand.
And how do you think throughout history, how do SIP homes perform against natural disasters compared to traditional stick frame homes?
Yeah, good question. As a consulting engineer, we're the ones that get called up when there's failures. There hasn't really it's not very often. It's not very often we get a failure in a stud frame house. I don't know of a structural failure that was due to a SIP wall panel or roof panel, as long as it was properly installed, like no errors by the contractor and it was waterproofed properly and whatnot. So I'd be willing to say that they perform equally. And I mean, I'm stamping projects every single day, putting my engineer stamp on projects. They're designed with SIP panels, and you know, I wouldn't be doing that if there's an issue. If there's a history of failures with SIP panels, I'd probably stop designing with them. But they perform really well. The lab tests prove that, and it's actually very comfortable going ahead and put my seal on those drawings.
And Troy, because they are much lighter weight buildings than traditional stick frame, wouldn't this be an advantage against certain natural disasters, in specifically, about hurricanes and earthquakes as well, because of its lightweight, it can be very easily anchored down to the foundation and prevent it like getting lifted off?
Sure. Yeah. I mean, what's one of the engineering theories, is it's called the equivalent static method. And it's a calculation that we as structural engineers perform to determine what's the shear caused by an earthquake. So seismic force is something that's in your building is directly related to the weight of the building. So with less lumber in your building and SIP panels being so light on the order of 4 or 5 pounds per square foot, your base shear is going to be less. And speaking of hold down hardware, the metal brackets that are used to prevent uplift and to prevent overturning and uplift of the corners of the shear walls and all that stuff. It's very simple to do. We're specifying the same Simpson hardware for our hold down brackets as we do on a conventional stud frame building. So it really is a direct substitution for SIP walls in a lot of cases, or for stud walls in a lot of cases.
Yeah, and just to add to that, and because a question we get a lot is, how do you use the same hold downs if you don't have lumber in your panels? They are like made of just that EPS core. And to that, I always mention that where there is a hold down, there is a lumber to attach to it, already installed in the panel, or to be installed on site connected to your hold down.
Yeah, that's 100% correct. And there's some tricks of the trade for constructability of SIP panels. And one of them is that hold down hardware. And like you said, Gabriel, you have to have a double stud on each end of your shear wall. And usually we need to tie that to the foundation with some sort of bracket. And we call it, there's basically 2 types of hold down brackets that you would use on the ends of those shear walls. One of them we call the strap style hold down, which is basically a metal strap that has a hook on the bottom of it that we embed into the concrete. And then the strap itself extends a couple of feet up alongside of the outside face of the wall, gets nailed into the SIP wall. The nails penetrate through the OSB facing and into the embedded stud. One example is the Simpson's STHD10. It's probably the most popular hold down strap that we specify at Eclipse Engineering, but they're simple. And the other type of hold down bracket is the boot style hold down. Now, those are a little more complicated for SIP panels. You would have to actually cut the facing off of the SIP panel where the boot style hold down would have to go to, and then install the boot style hold down, and then spray foam insulation around that boot hold down inside the panel, completely fill that void with foam, and then reapply the OSB face to the outside of the panel. So that's kind of labor intensive. So we try to avoid calling out boot style hold downs.
Sure. Troy, for an engineer that is just getting started on his first SIP design, what recommendations would you give him? Like, where can he find some information? And also, in some of our experiences, there is sometimes information that is not directly in the test report, but can be calculated to alternative means and methods. Can we talk a little bit about this?
Yeah, absolutely. Yeah, that's a good question. So if this is your first SIP project as a structural engineer, then the first place to start would be to download a copy of the SIPA code report and study all the load tables in there, because you're going to have a load table that has capacities for bearing walls and for shear wall capacity and for transverse loads with no reinforcement in it, and transverse loads with eye joists in it as well. So that'd be the starting point, because you can specify your panels very simply and easily just by using the code report. And what we do is we actually attach the full copy of the code report on the back end of our structural calculation booklet and refer to that code report from our calculations within the booklet. So fairly simple. But yeah, sometimes there's going to be situations where you need to engineer a SIP panel whose capacity is not included in the code report. Let's go back to the high snow load situation again, where you find that, okay, I've got a certain span that's too far for a SIP panel to do, even if it's reinforced with eye joists. Well, then you've got, you can reinforce it with lumber, say double 2x12s or 4 feet on center. And I can tell you that the capacities of that assembly are going to exceed the capacities of an eye joist reinforced panel. But hey, it's not in the code report. So what do? Well, there's established engineering theory where you can provide your own calculations, depending on the species and the grade of the lumber. There's structural properties for the foam, that are included on the first table in the SIPA code report. There's structural properties for the OSB that are included in the same report, and you can create your own calculations. And this is referred to as an alternate means and methods. We use this very often at Eclipse for situations that are not included in there. The alternate means and methods is the code path to use that is in the International Building Code. It's IBC section 104.11. And so that's what allows us to basically create our own custom calculations that are not already included in the code report. But, that's one way of doing it. I have another way I have another method, that we could talk about as well. But I've been talking for a while here, so I want to give you a chance to speak before I dive into the second method.
No, please dive in. I want to hear about it.
Okay. Well, and a second method, if you are a structural engineer, what you can do is you can treat the SIP panels as a deferred submittal. And so what this means is basically you specify that you want to use SIP panels for your walls and for your roof and for your floor, if it makes sense to do that. And then in your general notes on your drawings, you state that you want the SIP panels to be a deferred submittal and that you want it to be engineered by a third-party engineer. And that happens often. In fact, let's say like of the 500 projects per year that Eclipse Engineering does, most of those are as a deferred submittal from another engineer, the engineer of record. So the engineer of record can say, basically, hey, I'll develop these structural drawings, I'll specify everything, design the foundation, the columns, the beams, and let the SIP specialty engineer take care of the SIP engineering stuff. So it ends up landing on our desk, and then we specify the SIP panels for the roof, including all the embedded lumber, if any is needed, the SIP shear walls, and all the calculations for the out of plane pressures and the headers and whatever studs are needed inside the SIP panels to carry point loads from the roof or the floor, all that stuff. And then we provide calculations for that. And at the end of the day, we apply our engineering stamp on the SIP fabrication drawings. So you have a submittal that comes back to the engineer record that has our calculations and stamped drawings. The engineer record reviews it, approves it, and then submit that to the building department for your permit.
Awesome, Troy. Yeah. And if any engineer, has any more questions, they can always refer to us at Preflex. We rely a lot of Troy and his team, so we're happy to, make that connection and put you guys in contact. And just to my final question to you, Troy, a little bit about your experience in designing so many SIP buildings. What's the biggest project you've designed using SIPs?
Oh, wow. Yeah, there's been some big ones. It's really interesting because, SIPs have so many advantages, and one of them is the speed of construction. And we've done a few projects that, are very, very remote where there's a challenge on getting materials to the site and also the labor. You need less labor to construct a SIP building, but there's areas in the remote parts of Alaska where you can ship the SIP panels on a barge, but it can only get upriver for a couple of months out of the year because it's frozen, the other 10 months of the year. And we've engineered schools in Alaska where the total square foot of SIPs on the project, including the walls and the roof, is over 60,000 square feet. We did one in Antarctica that's under construction right now that, the barge left the port of Seattle and had to, it takes 2 months to get down to the McMurdo Research Center in Antarctica. And that one also was about 60,000 square feet total of SIP panels. There's been, warehouses and schools across the country, Arizona, Montana, Wyoming, and lots of projects in Washington and Colorado where, it could easily be, 40,000, 50,000 square feet of panel on one single project.
Wow, that sounds amazing, Troy. It is interesting that they use the panels in Antarctica, but I can see why with the quick drying times they need to be able to close the building up before it gets snowed in. So that seems like a very interesting project, and thank you for sharing that with us, Troy. We're getting to the end of the podcast, but we really appreciate you joining and sharing your knowledge on structural engineering with us. And this concludes today's episode of Building Better. Please go follow us on Instagram at Preflex Buildings, where you can ask questions, interact with us, and see what we're up to every day here at Preflex. Thank you for joining us, and we'll be back next month with a whole new episode of Building Better. I'm Gabriel Grossman. See you next time.